Okay, hello. We're going to talk about the rational root theorem. This is a theorem about polynomials and about the roots or zeros of those polynomials and what we can say about them in the specific case where the polynomial is a nice polynomial whose coefficients are integers. Okay, so there's a lot of ways to approach this, but maybe first we'll just start with an example. Okay, so take the following example. 15x squared plus 11x minus 14. And the goal is find the roots. And that is actually the goal of this entire unit that we're in, is to find the roots of polynomials and therefore sort of understand those polynomials. Okay, well, in this particular case, this is a very simple polynomial. It's a quadratic. And we sort of already know everything about quadratics that there is to know. We can do the quadratic formula. We can sort of always determine whether the quadratic has roots and what the roots are. So here, let's just find the roots of this quadratic and see if we can kind of learn anything. Well, in fact, this quadratic factors, so that's kind of nice. Let's factor it. There are a lot of ways to do this, but my way is like this. And, okay, I'm looking for diagonal products whose difference is 11, and 10 and 21, boom, there I found it. So that becomes 5x, 7, and 3x, 2. Okay, so that's 15x squared minus 10x plus 21x minus 14. I just checked that was true. Alright, so this quadratic factors, and in fact we say that this polynomial, f, we say factors over the rationals. Factors over the rationals. That might be a phrase that you've never heard before, because normally we would just say it factors, and sort of if it doesn't factor, then we just say it doesn't factor. But what we really mean when we say it factors is that it can be factored into some sort of nice things, and by that we mean sort of integers. And okay, when we say factors over the rationals, specifically we mean that these individual linear functions have kind of rational roots. All right, well, what are the roots? Of course, once we have the polynomial factored in this way, we can see that one root is negative 7/5 and another root is 2/3. All right, well, great. Negative, and sort of continuing to make some kind of comments over here, negative 7/5 and 2/3 are what we call rational roots. And that's because they're roots, and they are rational numbers. What does it mean to be a rational number? It means to be, it's a fraction, where the numerator and denominator are integers. Okay, that's just what a rational number is. Alright, well, you can't help but notice certain observations that we can make here, and one of those observations is that if you look at these two denominators, 3 and 5, they bear some relationship to this leading coefficient 15. And so let's just note that if you multiply 3 and 5 together, then you get that leading coefficient 15. And if you multiply this 2 and 7 together, here I'm kind of ignoring the negatives, then you get 14. And so the sort of most basic kind of way of thinking about the rational root theorem is just to sort of say, does this always happen? And loosely speaking, the answer is kind of yes. That when a polynomial, not just a quadratic, but any polynomial, has rational roots, then those rational roots in some sense come from factors that are like this. And if the polynomial has factors that are like this, then these denominators sort of come in some sense from these kind of linear factors, and therefore we can say that these numbers 3 and 5 are factors of the leading coefficient, and the 2 and 7 are factors of the constant term. Okay, so I won't write that down, I'll just say that out loud. 3 and 5, the denominators of the rational roots, are factors of the leading coefficient. 2 and 7 are factors of the constant term. Okay, Yeah. It's important to say factors and not just the observation that 5 times 3 is 15 and 2 times 7 is 14. That might lead you to think that if you just multiply these numbers, you'll get that number. Okay, well that's true in this case, but of course it's possible to give an example in which that's not so. So just take this function and just multiply it by 2. So now we get 30x squared plus 22x minus 28. So this is, of course, a perfectly legitimate polynomial. It's a quadratic polynomial. And, okay, what can we say about this polynomial? Well, common sense says that it has the same roots as f does, and that's just true. Presented with this polynomial out of the blue, you might first factor out a 2. That's the kind of thing that you learn in Algebra 1. And having factored out the 2, I now have this quadratic, and then I would just factor this quadratic as before. So I get 5x plus 7 and 3x minus 2. Okay, so what can I say about this this polynomial g? Well, it has roots, and those roots are negative 7/5 and 2/3. And okay, therefore, what is the relationship between f and g? Well, it has the same. F and g are very much related to they have the same roots, but also g is just f times 2. So if you think of the f function as being some kind of parabola, the g function is just that parabola sort of stretched out by a factor of 2, so it's sort of 2 times bigger. And you know, when you multiply 0 by 2, you just get 0, so the roots stay the same. But for our purposes right now, we notice that this polynomial also has rational roots, and here you can sort of see why you would want to be careful because now the observation is not that 5 times 3 is 30, but that 5 and 3 are factors of 30. And here it's not that 2 times 7 is 28, but that 2 times 7, 2 and 7 are each factors of 28. Okay, blah, 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 blah. Also, it is important so sort of like note, it's important to express your rational root in lowest terms. So of course 2/3 is a root of f. That is a fact. But 2/3 equals 200 over 300. Like, that's just true. That's a perfectly legitimate representation of this number, 2/3. But you would now not say that 300, the denominator, is a factor of 15. In fact, it just isn't. Nor is 200 a factor of 14. So this is a little bit subtle, right? So in order for this theorem to kind of make any sense, or this observation to make any sense, you know, sort of we insist that our rational roots, or maybe I'll just say our rational numbers, we insist that our rational numbers be in lowest terms. So if a polynomial has rational roots, then by putting that rational root in lowest terms, then we have this observation that the denominator bears some relationship to the leading coefficient of the polynomial, and the numerator bears some relationship to the constant term. Okay, good. So this was sort of the warm-up. Let me take a second and erase all of this, and then I will sort of state precisely the rational root theorem, what it is really saying. Because it is a kind of an abstract theorem that applies not just to quadratics, but to any kind of polynomial. So, all right, here we go. The rational root theorem, this is the statement. If P is a polynomial, if P is a polynomial with integer coefficients, okay, comma, and if P has a rational root. And let's be clear about what we mean to say that P has a rational root. Well, it means it has a 0, so let me just sort of now, in brackets or something, I'll say that it has a 0, and that 0 is a rational number. What does it mean to be a rational number? It means it can be expressed as a ratio of two integers. And so to say that P has a rational root is to say that there is some number of the form C over D such that when I plug it into P, I get back 0. That's what it means to be a root. And this is a rational number because C and D are integers and D is not 0. So this is the definition of what it means for C over D to be a rational number. This is the definition of what it means for C over D to be a root. And as we've said just a minute ago, this makes only sense if C and D are in lowest terms. In other words, you've reduced the fraction as much as possible. I'll say more about that later. Okay, if all of that is true, then finally I'm ready to kind of state the theorem. Well then, the denominator is the factor of the leading coefficient, and the numerator is the factor of the constant term. So then, D is a factor of the leading coefficient. That is the coefficient of highest degree of the polynomial. And C is a factor of the constant term. Okay. Good. Okay. I would like to make a note that this is a very restrictive theorem. First of all, it applies only to polynomials. So that's worth mentioning. This is a theorem about polynomials. So if you've got some kind of non-polynomial, this theorem has nothing to say about that. Also, it applies only to polynomials with integer coefficients. So that itself is a very restricted class of polynomials. For example, you might have some very disgusting polynomial. I'll give you an example over here, whose, maybe the coefficient of the cubic term is like some irrational number, like pi or something like that, and square root of 2, that's another irrational number. So here we go, right? That is a perfectly legitimate polynomial, but it is a polynomial whose coefficients are irrational, and so the rational root theorem has nothing to say about that. Okay. Good. And so this only applies to polynomials, and it only applies to polynomials with integer coefficients. And this theorem doesn't actually say that there is going to be a rational root. It only applies if, I'll put this in all caps, the polynomial has a rational root. And there is no guarantee that it does, a rational root. So, for example, here I'll maybe put in a box the kind of polynomial for which this theorem tells us nothing. There is another kind of polynomial for which this theorem tells us nothing. Here is one, x cubed minus 2, for example. What is this polynomial? Well, it's a cubic. In fact, it's the normal x cubed function, but it's just been moved down 2. So it's going to look, kind of like that. And it has one and only root, and the only root of this polynomial is cube root of 2. If you plug in the cube root of 2 here, then you get 0. Sorry, that's bad what I just wrote there. What I meant to say was the cube root of 2 is 0. Okay, so here is a kind of example of a polynomial with integer coefficients. It has only one root, one real root, and it's irrational. Okay, so in that case, this can certainly happen, and that means that the rational root theorem tells us nothing, because the rational root theorem assumes that the polynomial has a rational root. Okay, so if you have a polynomial, and your polynomial has integer coefficients, and the polynomial has a rational root, then this theorem guarantees some relationship between that rational root and the polynomial. Okay, so I am going to prove this, but I'm going to prove it at the end of the video because that's what I'm going to do. So let's assume that the theorem has been proved, and let's go straight to some examples, and then we'll see sort of the power of this theorem, and then we'll go back and prove it. Okay, be back in 1 sec. Okay, we're back. We are going to give an example right now of how one would use the rational root theorem. But really, the rational root theorem is a tool that is sort of mildly helpful in certain circumstances. The big picture is we want to find the roots of polynomials, and in general this is very hard. We're only going to be successful if the polynomial is kind of nice and it has kind of like a nice simple root. And once you're in the land of cubics, things are already sort of very hard. And so I'm going to backtrack a little bit just to kind of review some of the things that happened in class last week, because maybe it was a little bit rushed. And okay, we had these examples like this cubic here. It doesn't have any obvious kind of symmetries. It doesn't appear to be any opportunity to do factor by grouping or anything. So finding the roots, that's what we want to do, is going to be very hard. Okay, and how are we going to do this? Well, the background, which I'm going to sort of go into now for a minute, is, well, we did this already, but I'll sort of just repeat it. That if you give me some function, not just this one, but any one, and you divide that function by x minus k, that polynomial function, by x minus k, then you're going to get some quotient polynomial left over, plus some remainder. But the remainder is always going to be a degree less than the thing you're dividing by, and because if not, you would just keep dividing. And so if you divide by something linear, by a linear polynomial, then what you're going to get left over, your remainder, is going to be a constant. Okay, this is simply just what happens if you divide any polynomial by something of the form x minus k. And, okay, and of course that remainder will be over x minus k. Okay, so you do a division, you get a quotient, and you get a remainder. Okay, great. Well, then one may multiply through by x minus k, and if you multiply through by x minus k, you get that this function can be expressed as q times x minus k plus r. And this is the sort of more advanced way of thinking about what's going on. It's not exactly that you're dividing the polynomial by x minus k per se, but you're sort of factoring it into a product of x minus k, some quotient polynomial, and some remainder. I guess it's kind of like the same thing. Okay, well, focusing on this particular representation of the function, we can see a couple of things really quickly, which is that if you plug in k, something very interesting happens. When you plug in k, you get something times 0, and therefore you are left with r. Okay, this is what's known as the remainder theorem. And the remainder theorem says that if you plug a number into a polynomial, then what you get back is in fact the remainder after dividing that polynomial by x minus k. I guess I could write that down. So f of k, the remainder theorem says, f of k, the value of some polynomial function upon an input of k, is just the remainder after dividing f by x minus k. Okay, and so this is the remainder theorem. And I will note sort of one more thing, which is that if you should happen to plug in f of k and get 0, so sort of if, I guess I want to say here, if f of k is 0, this is now a special case of the remainder theorem, well, that means the remainder is 0. Then the remainder is 0, which is another way of saying that x minus k is a factor of f. Okay, this is called the factor theorem. And there are sort of multiple different kind of proofs of this, some possibly better than what I have here. But the factor theorem kind of summarizes and gives a name to an observation that you might find already to be sort of so obvious that you didn't even realize it was something to talk about. But if you give me some function and you tell me, so you give me some polynomial. I'll just make one up. 5x cubed minus 20x plus 1. This is going to be a terrible example. Hold on, let me do some math in my head. 135 minus okay, there it is. So, if I did that correctly, and who knows if I did, but I probably did, then, sure. Then I can now make some observation. Suppose I just happen to notice that 3 is a root. Actually, it is. Because if you plug in 27 here, you get 5 times 27 minus 60 minus 75, and I think 5 times 27 is 135. So this in fact is 0. Okay, so now that I know that 3 is a 0, that means the conclusion that I draw via the factor theorem is that x minus 3 is a factor. And that's not actually very obvious to me at all, but that's what the factor theorem says. The factor theorem says that if you divide this polynomial by x minus 3, maybe we should just do it right now really fast, right? Take 5x cubed minus 0x squared minus 20x minus 75, and you divide this by x minus 3, it must go in evenly, and here it just will. What do we get? We get 5x squared, 5x cubed minus 15x squared, so that's 15x squared minus 20x. I could have also factored a 5 out of all of these, but too late. Plus 15x. So it's 15x squared minus 45x, and geez, I hope this works out. Negative plus 45, so that's 25x minus 75, and you get a plus 3, so rather plus 25. So that's 25x minus 75. Okay, so indeed, we see a sort of a confirmation with a quick example that of the factor theorem. If a number is a root, then x minus that number is a factor, and sort of vice versa. Okay, but what we have seen is that this process of doing polynomial long division, though it's kind of fine in a way, that there is a much faster way, and the much faster way is to use synthetic division. So the new advanced kind of fast way to do this problem is to go 5, 0, 20, 75, and then it takes a matter of mere seconds to see, if 3 is a root. And how do we do that? We go like this. We go 5, multiply 3 times 5 is 15, add, we get 15, multiply, sorry, that should be negative 20, negative 75. So we get 45, add, we get 25, multiply, we get 75, add, we get 0. And notice that these coefficients, 5, 15, and 75, are the coefficients of the quotient. Alright, so this is what we spent all last class doing, confirming to ourselves that there's this thing called synthetic division, that it works, and by it works, what I mean by that is synthetic division just is the same thing as polynomial long division, as long as the thing you're dividing by is of the form x minus 3, or x minus some number. Okay, and so what does this all boil down to? This all boils down to the search for roots is just the search for factors. To find out what the roots of this polynomial are, I really just need to sort of do the division and see what goes in evenly. If something goes in evenly, then that number will be a factor. Okay, so that was perhaps an unnecessary 5-minute digression, but let's go back to solving this problem. The way to solve this problem is sort of just remarkably silly. And I want you to sort of feel how sort of stupid it is in some sense. I don't know what to do, so I'm just going to guess. I'm just going to blindly guess. And there is this thing called the law of ones. This is not a math law. This is a law of sociology, which says that 1 is often a root. And that's because, since we're blindly guessing, it would be annoying to blindly guess for a long time. And so people who have written these problems have often let 1 be a root, just so this process would kind of terminate. Okay, what does it mean to blindly guess? Well, we're going to check using the law of ones. We're going to check to see if x equals 1 is a root. And that sounds kind of tedious, but in fact, the synthetic division is just so fast that you can check in like 10 seconds. How do you do it? You write the coefficients, 1, 3, negative 18, negative 40. Over here you put a 1, and then you just basically just do it really fast. Ready? 1, you multiply, you get 1, you add, you get 4, you multiply, you get 4, you add, negative 14, you multiply, negative 14, and you add, negative 54. Okay, it did not go in evenly. But therefore 1 is not a root. In fact, what I have really just done, by checking to see whether 1 is a root, what I have really just done is divided by x minus 1. So what I can say right now is that this polynomial, this one that we're interested in, is of the form, or can be written as, x minus 1 times x squared plus 4x minus 14, and the remainder is 54. Okay, that doesn't really help me, but maybe it's important to kind of put this all together. That's what we're really doing. This algorithm is really just doing polynomial long division sort of very, very quickly. And these numbers are the coefficients of the quotient, and this number is the remainder, and we want that remainder to be 0. Okay, so I could keep just blindly guessing more numbers. But instead of just blindly guessing, let me apply the rational root theorem. And what does the rational root theorem say? The rational root theorem says that if you have a polynomial with integer coefficients, well, we do have a polynomial with integer coefficients, then any rational root, so any rational root of f must be in the following form. Well, what does the rational root theorem say? It says that the denominator must be a factor of the leading coefficient. Well, the leading coefficient is just 1, so that means that the denominator has to be a 1. And the numerator must be a factor of the constant term. Okay, what are the factors of 40? Well, there are kind of a lot. 1 and 40, 2 and 20, 4 is a factor as well, 5 is a factor, and 8, so I guess we just get all of these, right? 10, 20, 40. Okay, so the number 40 in fact has these 8 factors, and the logic here is, the first time maybe it's a little bit confusing. I don't know necessarily if this polynomial even has a rational root. But if it has a rational root, then the rational number must have as its denominator 1, in other words this is an integer, and the numerator must be some factor of 40. Therefore, oh, and by the way, all negatives are possible. Therefore, there are, I claim, only 16 possible numbers which could be rational roots of this polynomial. 1, -1, 2, -2, 4, -4, 8, -8, etc. 5, -5. These 8 numbers and their opposites. Okay, so the algorithm, such as it was from a couple minutes ago, which is just to blindly guess numbers, of course that's kind of an outrageous algorithm, it's not an algorithm at all, now has been reduced down to a slightly less outrageous algorithm. Now I have merely 16 numbers to check. And if I check all 16 and none of them work, then the rational root theorem tells me that if there's a rational root, it must be of this form. And so if none of these 16 numbers work, then I can say that this cubic in fact has no rational roots at all. And I can just stop guessing, and I can use some kind of numerical techniques to get like an approximate solution, or I could use the cubic formula or something crazy like that. Okay, so if we get that, then now we just get on the hunt. So what's the hunt? Let's try -1. If 1 isn't a root, maybe -1 is. Okay, so once again I sort of throw up the coefficient of the polynomial, and now I just perform the synthetic division algorithm on -1. So I get 1, multiply, I get -1, add, I get 2, multiply, -2, add, -20, multiply 20, but still that's -20. So that didn't work. So that was a sad face. Okay, let's try again. Now let's try with like, I don't know, 2 or something. 2 is a nice small number. In fact, it's kind of the next number in my list to try or something. So let's go. So I get 1, 2, 5, 10, -8, -16, that's -56. So that also doesn't work. So I'm like kind of really sad. I don't know, let's try -2. Well, I get 1, 3, -18, -40, and let's see, that's 1, -2, 1, -2, -20, oh, here we go, -2 times -20 is +40, and that is 0. So ding, 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 it took me 4 tries, 1 didn't work, -1 didn't work, 2 didn't work, but -2 did. And what do I mean by worked? I mean I divided through and I got 0. Just to be clear, what one gathers from this thing that we just did is that this polynomial is in fact just x plus 2, because that's really what we're doing when we do synthetic division with -2. What we're really doing is we're dividing by x plus 2, and what we get is x squared plus x minus 20. And the remainder is 0. In other words, it goes in evenly. In other words, x plus 2 is a factor. In other words, f of -2 is a root. Okay, so that solves this problem in the sense that if the goal is to find all the roots, we have now found one of the roots, but of course we have also factored the cubic into a linear and a quadratic, so now one could easily just do some techniques to find out what these are. I guess this factors as well, right, into plus 5 minus 4, so this would be x plus 5, x minus 4, I guess. Yeah. So, therefore, in fact, the roots of this cubic are -2, -5, and positive 4. Okay, good. What does the rational root theorem get us here? It takes our method of completely blindly guessing a bunch of small integer possibilities and says that there is actually kind of like a finite list of numbers to check, so just kind of check them all. Okay, let's do one more example. All right, example 2. Okay, this one's maybe a little bit more sort of reasonable. Here, once again, I have this, I have a cubic. Once again, my goal is to find the roots, and once again, there doesn't seem to be any way to do this, really. So find roots is what I want to do. Uh-oh, crying baby. Okay, how are we going to do this? Well, we're going to apply the rational root theorem. Pause this for a second. Okay, so have this cubic. What do we want to do? We're going to apply the rational root theorem. Why I think this is a little bit subtle is because I don't actually know that the function has rational roots, but if it has rational roots, then that's why I asked this question. Does f have rational roots? Answer, maybe. If there is a rational number, which when plugged into this function gives me back 0, then I can say something about it. What I can say is that the denominator is the factor of the leading coefficient. So a d is a factor of 3, and the numerator c is a factor of 25. And so what we make is this kind of chart of possible rational roots or whatever. And what are the possible rational roots? Well, we just consider all the numbers for which the denominator d is a factor of 3. Well, the only factors of 3 are 1 and 3. And the only factors of 25 are 1, 5, and 25. And so I need only consider, and all their negatives, numbers of the form 1, 5, or 25 over 1 and 3. In other words, what are all the numbers which could possibly be rational roots? Well, 1, negative 1, 3, negative 3, or sorry, no, that's not true. 1, negative 1, I guess we can do this different ways. 1, so 1 over 1, 1 over 3, so 1/3, negative 1/3, that's another possibility. 5, negative 5, 5/3, negative 5/3, 25, negative 25, 25/3, and negative 25/3. Okay, so this still kind of sucks because that is 12 numbers, but all we now need to do is just try all 12. And if we get lucky and hit one kind of soon, then great. But if we should try all 12 and none of them work, then we just give up. Okay, so good. Still, we should maybe use the law of ones. What is the law of ones? It says check to see if 1 is a root. So okay, let's go. So what do I have here? 3, negative 17, 35, negative 25, and we do this, we get a 3. So if 1 doesn't work, it means the problem was written by a sort of mean person, and that is in fact what happens. That doesn't work. Okay, we can try negative 1. Well, what do we get? Now, 3, negative 3, negative 20, 20, 55, negative 55, negative 80. Okay, so that didn't work either, but hopefully you're appreciating that it really does take just like 10 seconds to do one of these. Alright, so notice that if I didn't, this is a time to pause for kind of understanding, if I didn't have the rational root theorem in my back pocket, then at this point I would have no guidance as to what to do next. And what I might do is I might, try like 2 next to see if that works, right? Without the rational root theorem, that's what I might do. Try 1, try negative 1, try 2, try negative 2. Okay, but that is really completely blindly guessing. Notice that what the power of the rational root theorem is to exclude certain numbers from even consideration. 2, the number 2 is just not in the form, it's not one of these 12 numbers. It's not a number which has 1, 5, or 25 in the numerator and 1 or 3 in the denominator. Therefore, the rational root theorem tells me that 2 cannot possibly be a rational root of this polynomial, and therefore I should not bother or waste my time checking to see if 2 is a root, because it simply can't be. Okay, and so then we might go to like one of these other numbers. Okay, on a hunch, I'm going to try 5/3. And if I try 5/3, let's see what happens. you would have gotten there eventually. When we do this live in class, I let people kind of try a whole bunch of them, and it takes a few minutes to stumble upon the answer. But what we get here is 5. This is negative 12. What happens now? What is that? Negative 20. Yeah. And here I get 15. Multiply it 25, and that is 0. So now I am really happy because 5/3 works. And what does that tell me? It tells me that this polynomial is really x minus 5/3 times 3x squared minus 12x plus 15. And then if I want to, I can sort of, continue on and use, kind of quadratic techniques, so to speak, to find the roots of this quadratic. But at least when you have a cubic, once you find one of the roots, then you're really done with the hard part, because the other roots are just going to be roots of this quadratic, and we sort of know how to find roots of quadratics. Okay, good. If you want to stop watching now, that's very respectable. But I will pause for a second, and I'm going to come back, and then I'm going to prove the rational root theorem. And that'll take maybe 20 minutes, so watch that if you want. Okay, bye. Okay, so if we're going to prove the rational root theorem, first we need some background number theory. So there's some sort of very low level facts about numbers that probably you've never been taught before, or at least in school. So here we go. We have this symbol. We say, we write it like this: A divides B. We pronounce this A divides B. And there are kind of many ways to say this. This is true if A goes evenly into B. That's kind of a 5th grade way of saying it. A is a factor of B. A is a factor of B is another way of expressing this. B is a multiple of A. These are all just synonyms for each other. Is a multiple of A. And maybe the best way of saying it is just to give sort of the definition. What does it mean for A to divide B? It means that B is in the form K times A, for some integer K. Okay, good. So just to be totally clear, what's an example? Well, 5, divides 35. 5 goes into 35. 5 is a factor of 35. 35 is a multiple of 5. And 35 can be expressed as 5 times 7. So there we go. Okay, so with that little bit of notation, there's more. A and B are relatively prime. Also, people say coprime or coprime. If they have no factors in common. If they have no factors in common. Okay, example? Well, take the example like 14 and 15, for example. Neither of those numbers are prime, but 14 is 2 times 7, 15 is 3 times 5, so they have no factors in common. Okay, so we have 3 little theorems. I'm going to squeeze them onto the board. Let's call this basic theorem, number 1 or whatever. And I'm not really going to prove these. I'm just going to kind of say them with a sort of casual explanation. So if A and B are relatively prime, and A and C are relatively prime, conclusion: A and BC are relatively prime. Okay. If A and B have no factors in common, and A and C have no factors in common, then when you multiply B and C together, you get the number B times C. Well, B times C must consist of a bunch of numbers, and none of those numbers have a common factor with A. Okay, so A and the product of 2 numbers for which A is relatively prime are relatively prime. Okay, good. Hopefully that was pretty clear. All right, basic theorem number 2. Basic theorem number 2 is, I think, kind of just an extension of basic theorem number 1. Here's what it says. If A and B are relatively prime, then A and B to the n are relatively prime. Alright, well, once again, if A and B have no factors in common, then what is this number b to the n? It's just b times b times b times b times b. So there's going to be a whole bunch of factors in there, but none of them are factors that A has either. Okay, you could think of it as just an application of basic theorem number 1 in which b equals c. That's how you would get that a and b squared have no factors in common. And if you just keep repeating that over and over again, a and b cubed have no factors in common, a and b to the 4th have no factors in common, etc. Okay, and basic theorem number 3 is that if a and b are relatively prime, if a and b are relatively prime, and a divides bc, then I conclude that a divides c. Okay, what does this say? It says, look, a goes evenly into this number b times c. But also, a and b have no factors in common. So if a and b have no factors in common, but a goes evenly into b times c, then a must go evenly into c. The only way a is getting into this product is because, in fact, c is a multiple of a. b certainly isn't a multiple of a because, in fact, a and b have no factors at all. Okay, these can all be proven if you want to, but that is sort of not part of this course. Hopefully I've justified them as being sort of intuitively plausible. Okay, I'm going to pause for 1 second and then we'll be back and we'll just prove this theorem. Okay, we are back. We're going to now finally just prove the rational root theorem in general. Okay, what does it mean to prove this sort of in general? I want to show that in general, for any polynomial whatsoever, of any degree, and any possible kind of coefficients, if it has a rational root, then the rational root must be of a certain form. Okay, so if I just take, how do I prove something about all polynomials with integer coefficients? Well, I need to take a kind of a generic polynomial with integer coefficients. So I want this polynomial p that I now investigate to be sort of a polynomial of kind of arbitrary degree. So let's say that our arbitrary polynomial has degree n. Okay, and if it has degree n, then I have to so what does that mean if this polynomial has degree n? Well, that means it's a polynomial with a whole bunch of terms that the highest degree term is x to the n. But I have no idea what the coefficients are. Okay, so in order to, this kind of gets technical now, because in order to do this in general, I need to consider sort of arbitrary coefficients. So okay, so if this is a nth degree polynomial, then the leading term will be of the form x to the n. I don't know what this coefficient is, so let's just call it a sub n. So the subscript refers to, a sub n just refers to the coefficient of the nth degree term. Okay, and now there is an n minus first degree term, and naturally I will use the coefficient a to the n minus 1, I will use that symbol to refer to that coefficient. Okay, so hopefully this is pretty clear, and then we dot down to let a1 be the coefficient of the degree 1 term, and then the degree 0 term is a sub 0. Okay, and just off here in the margins, let me issue some sort of clarifications. One clarification is that all of these coefficients are integers, because that's what it means. That's one of my assumptions. So a sub I is an integer. But there's another kind of little subtle fact that I realize now, only at this point when things are getting serious, that I need to insist upon. One thing I need to insist upon is that a sub n be sort of not 0. after all, I'm going to say something about, quote unquote, the leading coefficient. Well, I need to make sure that the leading coefficient is not 0. If the leading coefficient is not 0, then it means if the leading coefficient is 0, then it's actually just not an nth degree polynomial at all. Okay, so when we say that it's that the degree of the polynomial is n, that means something. It means that the coefficient of the nth degree term is actually not 0. But also, my theorem is going to have something to say about the constant term. So I better insist that there is a constant term. So I also want to insist at the outset that a sub 0 is not 0. If it is 0, then the rational root theorem is just not applicable. Okay, that didn't come up until now, but in some ways it just kind of makes complete sense. After all, if you give me some polynomial, and it looks like this, and there's no constant term at all, well, if the overall goal here is to find the roots of this polynomial, then the first thing I should do is to factor out an x, and I'm left with like this, okay? And now I will just continue my sort of root finding algorithm on the remaining polynomial. In other words, this is to say that if the big picture goal is to find roots, then polynomials with no constant term are a little bit silly, because one may then just factor out whatever the highest power of x is that goes into all the terms, and then you're left with a polynomial that does have a constant term, and then you just sort of perform the rational root theorem, on that leftover. Okay, good. So, having said all that, notice that we haven't actually done anything yet. What does the rational root theorem say? It says, if you have a polynomial with integer coefficients, check, we have one. And if it has a rational root. Okay, so I need to now suppose that P has a rational root. So suppose P has a rational root. Well, what does that even mean to say that P has a rational root? Well, in brackets I shall clarify. It means that there is some rational number of the form C over D such that when I plug it into the polynomial I get back 0. And I need to clarify that this is in fact a rational number. So that is, I should say that C and D are integers, and also that D is not 0. So far this says that there's a rational root, but remember that previously we said that this theorem only makes sense if this fraction is in lowest terms. And so I will insist that this fraction be in lowest terms, and based on our vocabulary from 10 minutes ago, I can now express this fact a little bit more precisely. I can say that C and D are relatively prime, that they have no factors in common. If they did have factors in common, C and D, then you should cancel those factors and therefore put the fraction in lowest terms. Okay, good. Having said all that, I'm now ready to state what the theorem says. What does the theorem say? If you have a polynomial with integer coefficients, if you have a rational root, then the denominator, D, must be a factor of the leading coefficient. In other words, D must divide a sub n, and C, the numerator, must be a factor of the constant term. Okay, so far, everything we've done, we haven't actually done any argument yet. We just kind of set the problem up very precisely with all of our kind of notation. Now we know what to do. We have to prove these two sort of basic number facts. All right, how are we going to do this? Well, there's basically only one thing to do. What do I sort of have to work with now? The only thing I have to work with is I got a polynomial here. Maybe sort of put a box around it or something. And there's pretty much only one thing I know about this polynomial. What I know about this polynomial is that when you plug in C over D, you get 0. And from these two sort of facts, I need to extract this relationship between C, D, A sub n, and A sub 0. Okay, well, I'm going to do the only thing there is to do, which is just plug this number in. Okay, so what is P of C over D? Well, when you plug this in, you just get a big ugly mess, right? Don't be scared. You get A sub n, C to the n over D to the n, plus A sub n minus 1 times C to the n minus 1 over D to the n minus 1, plus, okay, and just in general, like I'm just plugging in C over D everywhere we see an X, right? So zoom, 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 and then we get like A sub 1 C over D plus A sub 0. And when I do that, I get 0. Okay, this makes me slightly happy because this is now I got a statement to work with, right? This is a sort of nice kind of statement here. I don't like the statement so much because it has a lot of fractions in it. And the fractions are kind of annoying or something. So let's do one more step, which is to multiply both sides by something which will kill all the fractions. And I need to multiply by sort of like the biggest fraction, which is d to the n. Okay, so now I'm going to multiply both sides of this equation by d to the nth power. And if I do that, I get this really nice statement that says, right here, a sub n c to the n plus, if I multiply this by d to the n, all of those cancel except for one extra d, so I get a sub n minus 1 c to the n minus 1 d, plus, and here I get a sub 1 c times, if I multiply by d to the n, one of them cancels, but the rest are still there, and a sub 0 d to the n equals 0. Okay, so this, if you're not used to this kind of thing, and you're pretty much not, then this just seems like a hodgepodge of extremely confusing kind of notation, and okay, that's just because we're trying to prove the theorem in general. It's what makes it so hard. It's very abstract. But notice the kind of low-level simplicity in what we have achieved here. All these coefficients are integers. C is an integer. D is an integer. So this entire statement in purple now is this like very, very simple statement. It is a simple statement that involves sums and products of integers. Okay, so all this polynomial stuff is gone, and I can just kind of focus on what matters, which is like this statement here. Okay, and what can be observed from this? Well, one thing that I notice is that almost every term here in the middle has C's and D's in it. Except this one has no D's, and this one has no C's. And so, what we can do here is kind of split this problem in two. And on the one hand, I want to sort of do two different algebraic things to this thing in the purple box. On the one hand, I want to move this one term that doesn't have any C's in it over to the other side. Okay, so let's just do that right now. A sub n c to the n plus a sub n minus 1 c to the n minus 1 d plus a sub 1 c d to the n minus 1 equals negative a sub 0 d to the n. Okay, what did I do? Almost nothing. I just moved this term over to the other side. I subtracted it over there. Okay, but then I also, in a kind of analogous move, want to do the similar thing by moving that guy over to the other side. So now I get, kind of got to keep a break here, a sub n minus 1 c to the n minus 1 d plus a sub 1 c d to the n minus 1 plus a sub 0 d to the n equals negative a sub n c to the n. Okay, and so now maybe I'll make sort of a more of a vertical line. All I did was take this thing in the purple box on the left, side here, I moved that term to the other side, and on the right side here, I just moved that first term over to the other side. Okay, but now I can make some observations. Here's my observation. Every number on the left-hand side of this equation is a multiple of c. In fact, I can even factor a c out. You don't even actually have to do this, but it makes some people feel better. So what am I doing? I'm factoring a c out of every term here on the left equals negative a sub 0 d to the n. Okay, why is that helpful? It's helpful because I can now conclude something. I can conclude that this left-hand side here is in fact a multiple of c. Every number on the left-hand side of the equation is, the left-hand side of this equation just is a multiple of c. But if the left-hand side of this equation is a multiple of c, then that means that the right-hand side must also be a multiple of c. Okay, in other words, I conclude that c is a factor, or rather that c divides a sub 0 d to the n. Okay, but now I go back to my fact that c and d are relatively prime, because the fraction is in lowest terms. Since c and d are relatively prime, c and d have no factors in common. If c and d have no factors in common, then c and d to the n have no factors in common either. And putting together those sort of three basic number theory facts from 15 minutes ago, if c and d to the n have no factors in common, and yet c divides a sub 0 times d to the n, I conclude that in fact c must divide a sub 0. And that is one of the two things that I set out to prove. The numerator must be a factor of the constant term. And over here, we just do it again, right? Every term on the left-hand side of this equation has a d in it. You don't even have to do this, but if you want to, you can factor out a d. And I'm just dropping one power here. Okay. And now I note that on the left-hand side here, that because I've explicitly factored out the d, this is certainly a multiple of d, this entire left-hand side. But if the left-hand side is a multiple of d, then the right-hand side is also a multiple of d. And if that's a multiple of d, then it means that d is a factor, d is a factor of a sub n c to the n. But now, once again, c and d are relatively prime. C and d have no common factors. If c and d have no common factors, then neither does d have any common factors with some power of c. And so if d goes evenly into this product, d must go into a sub n. So d divides a sub n. And this is the other fact that the rational root theorem tells me. That the denominator of the rational root, if there is one, must divide the leading coefficient. Okay, so that's the entire proof. It's not even hard, it's just very, very abstract. And so, okay, if you watched all the way to the end, I think you got smarter and got some kind of exposure to sort of advanced kind of math. If you didn't watch to the end, it's not the worst thing in the world. So, goodbye, see you all next week.